My name is Lorenzo Villaggi, and this is Daniel Nagy. We're both designers and researchers within The Living, an Autodesk studio based in New York City. And today we're going to talk about this class, Generative Design for Architectural Space Planning. So generative design is a concept and its implementation for the design of this year's AU exhibit hall floor layout. So before diving into the content of the class, we're going to give you a quick overview about who we are and what The Living is about. And the class is divided in two parts. The first half is going to be more of a high-level presentation of the project, and then we will give a live demo of generative design in action, showing some of the files and algorithm that we use to generate the floor plan. The Living is a research and design studio based in New York City. It's a small group made of 8 people, including our founder and principal, David Benjamin. The work lies at the intersection of technology, culture, and synthetic biology. In 2014, we have been acquired by Autodesk, and since then we've been part of Autodesk Research, also known as OCTO, Office of the CDO, and together with other great research groups, we've been investigating new ways of the future, how to tackle the future of making things through architecture. Some of our clients, most of our clients are very different in nature. They vary from private corporations to local governmental entities to public and cultural institutions. Following the acquisition, The Living operates as a hybrid entity within the research division. On one side, we function as an experimental architectural firm and deliver projects of varying scope, scale, and degrees of interactivity with the public, and varying degrees of permanency. On the other side, we also pursue this research aspect of our firm. And so what we do at the end of each project that we deliver as a service, we try to extract what we think is the most interesting and forward-thinking type of piece of technology, workflow, or ways of making architecture. And these extractions, let's call them like this, become the foundation for independent research trajectories that often become papers. And in this past year, we published several research papers that we published in venues that you probably are all very familiar with, like Acadia, DMS, CMOD, just to name a few. So we'll start by trying to define what generative design is and explain some of the ideas and concepts behind it. Generative design is a hybrid design strategy that combines artificial intelligence and human creativity through an automated design workflow to discover high-performing and unexpected design solutions. And these are some of the latest applications of generative design on real-world projects. Typically, generative design is constituted by 3 key components: a generative model that defines a wide design space of valid design solution, an evaluative component that automatically scores and assigns numerical values to each design solutions, and these numerical values are then provided to a meta-heuristic search algorithm that uses these scores to learn and adapt over time, generations after generations of design, to create better, high-performing designs over time, and in other words, evolve designs over time. Generative design follows the ways living forms have been designed, and the way nature designs is through evolutionary processes. The key aspect of these processes is the role that species play and how they develop over time. They're encoded with unique genotypic and phenotypic properties Through steps of mutation, crossbreeding, and selection, they evolve and adapt over time. So given this context, we can better understand the underlying principles of generative design. And in this way, we can define the generative model as what is being called by some experts the expression algorithm. That is pretty much a mapping. It's about the mapping of the relationships between the genotypic state and the phenotypic state. And then we have a genetic algorithm that uses, again, the principles of mutation, breeding, and selection and competition to evolve and adapt designs over time. While mutation and crossbreeding happen at the genotypic state, at the genotypic level, so the main inputs of the model, the concepts of selection and competition take place at the phenotypic level. One important key aspect about generative design is that it behaves as a black box. So it doesn't know anything about the problem that it's trying to solve, and it's not encoded with any preconception by the human user. Therefore, it just learns and adapts over time through the information that it retrieves by the solutions that it generates over generations. And because of these concepts, generative design can be placed within the realm of artificial intelligence. So moving forward and diving directly into the project, we start with the problem formulation and project formulation. So typically, during the design process, you look at examples of what has been done in the past before, and you generally base your design decisions on rule of thumbs, what are typically called rule of thumbs, or your simple intuition. For example, in this case, from the floor plans of the exhibit hall from AU 2016 and 2015, you can see a reliance on a symmetrical arrangement of the pavilions and the arrangement of key booths and pavilions next to access points in order to ensure and guarantee some sort of exposure, knowing through intuition that lots of people will go through access locations. So what we asked ourselves was, what if you started with fewer preconceptions about these design ideas, and your goal was simply to discover new and unexpected design solutions? We had three primary drivers at the beginning of this project. One was turning AU into a physical signifier of cutting-edge design methods. Two, immerse AU visitors into a literally generatively designed space. And finally, increase and redefine in a way the value of the booths through a data-driven process. Moving forward, we'll now show the sequence and the steps that we took to apply generative design to this project. There's a pre-generative design phase that requires the gathering of unique data about the project, and that can be encoded in the form of constraints and requirements into the model. And in this case, we, through a collaboration with the AU gallery folks, we gathered requirements about square footage for each pavilion and booth, and requirements about adjacency relationships between each program. Constraints can also be geometric in nature, and these were as well encoded into the system. On one side, we have the fixed boundary of the exhibit hall, the location of the columns, egress access locations, toilets, and vertical circulation. But constraints and requirements can also be based on design decisions. So together with the AU gallery team, we understood that there was a strong desire to have a portion of the Autodesk Pavilion next to the two access points that connect the AU Kino Hall and the exhibit hall. And so the big green area is just like a portion of the Autodesk Pavilion that then was allowed to grow and expand during the generative design phase up until it could meet its target square footage. Again, I wanted to stress the importance of what we've been calling the expression algorithm and the mapping between the genotypic state, which represents the set of inputs that the expression algorithm uses in order to translate that set of information into a fully morphologically expressed model, which is its phenotypical state. And more simply put, we had as genotypes a series of inputs. There were 23 numerical values. 3 values were used for the parametrization of the geometric model, and then 23 values were used for the parameterization of the placement of the program. And through a series of operations, as outputs, we had 2 design goals, buzz and exposure, which I'll explain more later. Our geometry system is divided into 2 main steps. At the top portion of this diagram, you can see all the geometrical steps, and at the bottom, the parameterization and placement of the program. The geometry steps are a series of subdivision of the entire layout space, from the definition of the fixed areas and geometric features that do not change throughout the generative design process, to the generation of 3 main avenues, which are fully parameterized and can move along the edges of the boundary hull, and these define an initial subdivision of the hull into macro regions. Then we have a series of streets that grow out of the avenues to further subdivide the macro regions into smaller regions. And then finally, each smaller region is discretized into cells through grids of varying orientation. Following the geometric steps, we have the placement of the programs. So each program is represented as a seed, as you can see on the left image, with red dots and blue dots. Each seed, through a series of steps, grows into cells through merging operations, and the growth continues up until each program reaches the target square footage. And in the final step, every cell that has not been merged becomes space available for boots. One important requirement of the expression algorithm or the design space model is to be computationally cheap, so fast to be executed. And our model was very fast and pretty inexpensive to compute, especially because it was based on a novel graph data structure that we used for the merging and subdivision operations. One important step of the generative design sequence is specifying and designing measures or design goals. And the 2 that we used were what we've been calling buzz, or the measurement of the amount and distribution of high activity zones throughout the entire floor plan, and exposure, which is the measurement of the proximity of each booth to these high activity zones. The visualizations correspond to the way we're getting feedback from the model about buzz and exposure. For buzz, we had a web of red lines with varying thickness, and for exposure, a gradient from white to red, which corresponds to low exposure to high exposure. Again, as mentioned earlier, a critical aspect of generative design is the relationship between genotype and phenotype. And because of that, we have developed a series of analytical tools to understand the quality of the design space. So it's not enough to just put together all the 3 components, generate, evaluate, and evolve, but there's also a lot of time put into calibrating how these components work together. And the metrics that we're trying to evaluate through this visualization system, which is low-resolution sampling of the design space, using solely the three inputs for the three main avenues, which we realized were the most important ones that had the greatest effects on the model. The two metrics were a range between bias and variance, which is a measure of the degree of variation or heritability of the model. While a high bias model is too simple to be used, a high variance model is too flexible. So we have lots of invalid designs. The other metric is a range between complexity and continuity, which measures the ability of the expression algorithm or the design model to generate a design space with unpredictable, non-intuitive solutions. A model that is not complex enough is not worth optimizing, as the result can be easily determined. So once the whole setup has been completed, we're able to run the optimization. And for this project, we generated over 30,000 solutions, 100 generations with 320 design solutions per generation. And as you can see from the scatter plot animated here with purple dots showing young designs and blue grayish dots, older designs, you can see how the materialistic search algorithm is learning over time and improving the performance of the design solutions. By exploring the front of high-performing designs, we're able, together with the main stakeholders of the project, to nail down a smaller subset of high-performing designs that were not only really good as far as the numerical outputs of the design solutions, but through in-house web app that was allowing us to explore the designs, we're able to visualize the designs and observe qualitative properties that not necessarily the generative design workflow was capturing. This is a brief overview and showcase of the Explorer app that we were using. As you can see, you can sort and filter designs according to what you're trying to look after, color-coded by the different metrics, change the size of the design points if you have an additional dimension that you want to visualize. And as you hover over every point, you can see the corresponding design. So these are three of some of the designs that we ended up selecting, and ended up selecting one that showcased a particular distribution of the programs that suited the requirements of the AU stakeholders, and showed a particular arrangement of the paths within the main Autodesk Pavilion that created this sort of wedge that funneled nicely the AU visitors from the keynote hall to the rest of the exhibit hall layout. This series of images are showing the progressive refinement of the design solution from, oops, Siri coming out. The series of refinement steps from, sorry, someone called her. The series of refinement steps from the raw output from generative design to intermediate refinement that we did in-house to the final design that we delivered to the AU stakeholders. And as you can see, we used the traffic paths, the high traffic paths, to size and determine the main streets and streets and avenues of the final design solution. And then finally, the space that you guys have probably seen earlier today that the contractor of the exhibit hall have refined themselves, making sure that the plan was meeting all specific requirements that may have not been captured by the workflow. Some final notes about this overview. We had three main drivers: turning AU into a signifier of cutting-edge design methodologies, immersing AU visitors into a space that was generatively designed, and most importantly, trying to understand how to redefine the value of the booths through and increasing them through a data-driven process. Ultimately, this process, generative design, allows you to discover unexpected novel designs, navigate trade-offs between high-performing designs, sketch goals and constraints rather than form, and it's a new form of co-design between human and computer. So trying to get as close as possible to a truly CAD software as Negroponte would have desired. And finally, there are a couple of references that have been very important for us during the development of the project, and some of the papers that we published where we were giving a more in-depth technical description of most of the key points that I touched upon during the presentation. So this was the first part of the lecture. We can stop for a minute and see if you guys have any questions in the meantime before we move forward with the technical demo. Yeah.
So do you have a method to actually map how the space is being used and compare it to what your generative design program predicted?
Sorry, could you repeat the question?
Do you have a way to map how the space is currently being used and juxtapose that with your prediction?
Right. Yeah, that's a really good question. Another team within Autodesk Research started this project called Project Anya, which is about measuring traffic flow through computer vision. And the great thing about generative design is, because of its modular nature, it allows the user to input new pieces of data, like new information about how people navigate the space, and update the way we make the simulations, for example, how we were measuring buzz and exposure, and eventually get closer and closer to what the actual behavior of traffic flow is. So yeah, definitely. It's an iterative process in itself where you can constantly update it through real-world data that we collect. Yeah.
Can you talk a little bit about where you as a human interacts with this generative process? Are you stopping every X number of iterations and evaluating, or are you looking at it all collectively at the end? How do you interact with the output?
Yeah, that's a great point, and we're still trying to. There's no clear standard about how the interaction between the human and the machine should take place. For this specific project, well, first of all, in general, for generative design, there's a design agenda that is embedded into the design system, and that happens mostly into what we've been calling the expression algorithm, or the model that generates the wide design space, and that requires design expertise, and lots of creativity goes into there. If another designer would have developed this system, it would have been completely different. It's not an objective result. So the human input in that phase of development is very, very hands-on. It definitely requires a few cycles of testing of the entire workflow for the calibration that I was mentioning at a certain point, the design space analysis. That requires to run DOEs, or some low resolution sampling of the design space in order to calibrate all these different modules. You don't want a highly complex design space because the search algorithm might not be able to find better and better designs very easily. You want that sweet spot between complexity and continuity, but you want also a sweet spot between bias and variance, which is the design agenda that we were talking about before. But once that is set up, you allow the computer to suggest you design solutions that you would have not expected by yourself. And only at the end, in what we've been calling the post-generative design phase, the human comes back in heavy-handed in order to refine the design solution. Because what generative design gives you ultimately is a design strategy that the human needs to work on and further develop the design. Yep. This project, I believe, we started it in February, March, I think, and early April, I believe, it ended. So it was a very fast-paced, quick turnaround. Yep. Definitely. There are definitely many other materialistic search algorithms. We specifically use the GA or the MOGA because it works really well with architectural problems that are not very well defined by nature, and they work really well with objectives that are higher than 2 or 3. This is a very specific case where we had only 2 objectives, but generally we have 4, 5, 6. For example, from the Van Wijnen project that was presented earlier this morning, there were 7 objectives that we were using. And to our experience, GAs are the ones that perform the best with that number, the quantity of design goals, but maybe either Dan or Dale, our computer scientists, can talk more about other alternatives to the GA, but that's the one that we've been focusing on the most. This whole process was done merely in Dynamo and in conjunction with in-house optimization platforms and in-house web application to navigate the design space.
Yeah, I'll show a little bit under the hood in the second part.
Yep.
If you should look at applying to urban scale, how we factor in human behavior and maybe social issues. How then description itself?
Yeah, that's something that we think is very important for generative design, and we tackled those kind of not issues, but those facts of the real world in an earlier project on the new Autodesk offices in Toronto at Mars. We took into consideration social behavior and social interaction and what people wanted about the space and encoded that into the system. So we had a series of metrics that were directly derived by a survey that we used to understand what people wanted. So again, because of the modularity of the process, like any kind of real world data can be embedded into the system. And if we were to tackle an urban type of project where we wanted to embed that kind of data, the only obstacle would be getting that data, how reliable the data is, and who would give it to us. But if it's available, yeah, this is a system that can definitely welcome data sets from real world. Yeah. So this one.
Yeah, so in this case, we ran on the local machine, and we were able to run several iterations of the test as we refined the model. Because the model was very quick to compute, we were able to do that just within a few days for this experiment. But the thing with genetic algorithms and a lot of other meta-heuristics, you can actually parallelize the process quite well. So if we're looking at like 200 generations of 100 designs each, you can parallelize those 100 designs very easily because they don't rely on each other, and you compute in batches. So there's definitely a lot of potential for speed gain in that way. But I would say that, you know, as with all things, when we're computing many, many designs, it's really you're going to hit that wall very quickly. So instead of investing a lot of time and effort into parallelization, we've actually invested a lot of time in making the model compute faster. And so you see that kind of trade-off where if you can reduce the computation time of each design by half, you do speed up twice the process. So the things that Lorenzo described in terms of how we specified the algorithms that do the subdivision and being very careful to look at all those processes and optimizing them, for us has been more effective. Yep.
Is it possible to achieve something like this or similar, just using project vector plus Dynamo plus maybe some AI library?
Yeah, I'm actually going to show a little bit under the hood of the tools we use. It's very Dynamo and scripting based. So yeah, it's a very similar process. You'll see. Should we transition maybe to the second part? And we'll save some time at the end for questions too, once we show some of the under the hood things. So if you have any other questions, save them. My name is Daniil Nagy. I work with Lorenzo at The Living. What we wanted to do in the second half is show a bit. How do I switch? Is it the red button?
Okay,
great. Cool. So we wanted to show a little bit under the hood of how we develop these generative design solutions and show you a little bit of the process and the tools that we use. And I just want to start by saying that what I'm going to show you includes work from a number of people in our team, some of which are here in the front row. So Dale, Damon, Ray, and also Jim, who's doing something else right now at AU. So we're a kind of very collaborative design studio. Everyone's involved in creating different portions of these workflows. So I just wanted to give a little shout out there. Before I begin, I just wanted to reiterate some things that Lorenzo talked about, where when we design these kind of workflows, we're not thinking really of developing general software solutions for design problems. We talk a lot about automation. You saw the keynote this morning. We're still at the level, I think, where right now technology and AI and software tools can really help us push our possibilities with design, but there's still a large human aspect to it. So to get to your question as well. So we really look at all these things as design problems, but maybe augmented by some kind of computational systems. But we're all designers in the studio, and we really address this as a kind of design problem approach. But instead of designing a single object or solution in 3 dimensions, our task is to design the multi-dimensional design space of all the different possible solutions that are valid, and then allowing the genetic algorithm to explore that space to find more or less good solutions and actually reveal those solutions to us so that we can consider them. So that's how we really look at the role of these genetic algorithms or other AI systems, is just presenting to them a very well-defined space of exploration, and then using that technology to explore some parts of that space that we might not explore otherwise. Okay, so when we do this, we rely on several different tools, and the focus of these tools is flexibility, because all of these workflows are more or less custom to address the specifics of different design projects. So instead of looking at a single solution which will give us magically the final design, we really need tools that are flexible, that allow us to craft custom workflows and custom solutions for different projects. And in order to do this, we really rely heavily, in this case, on Dynamo, which is a node-based visual programming language that allows you to sequence together different aspects of the project, different computational steps, and basically, through this node-based workflow, craft the entire design space that Lorenzo described. So just so I know, who's familiar with Dynamo already? Awesome. So you guys know what I'm talking about? That's great. So let me just dive right in there and show you how we craft this design space in this example in Dynamo. So this is a kind of stripped-down example. It contains a lot of the same functionality as what we had in the final model for AU. But as you guys know, working with Dynamo or Grasshopper, some of the solutions very quickly get really crazy. So just to give you a kind of high-level overview, we kind of stripped away some of the more specific elements of the design and focused on just the basic geometry and evaluation steps. Okay, so here you see a kind of generic plan layout. We have the specification of a plan boundary. This can be convex or non-convex here. and then the subdivision through a few parameters that Lorenzo described of the space into smaller parcels. So we have the specification of 2 main circulation avenues. In the AU example, we had 3. And then the location of, I believe, 3 program nodes within along the avenues, and then the routing of traffic from 2 entry points into the space to the 3 programs. And you see some of the visualization in Dynamo of the buzz metric, which is visualized as the red lines and nodes, which actually directly visualizes the predicted amount of people circulating along those paths. And the visualization of the exposure metric in this orange, which is showing the parcels in the floor plan that are most exposed to traffic. All right. So here you see the graph that's generating that, and this is like a one-to-one visualization of the design space, where on the left side you have the design inputs that are the genotype, which control the expression of each design, of each plan in this case. Those inputs gets passed through a number of nodes that create the geometry, they evaluate the geometry, do the visualization, etc. And in the end, you have 2 metrics in the blue containers here, which are the actual computation of the buzz and the exposure scores. So let me just walk you through a few of these parts of this definition. So we start here with the inputs. As Lorenzo described, we have 2 avenues, but they're parameterized with 3 input parameters. We have 1 avenue starting at the main entrance, and then this point is parameterized along the opposite edge. And then the second avenue is parameterized as points along both edges. And if we change one of these inputs, of course, you see the graph update. So I move this avenue slider to the left, so this avenue is changing here, and everything is updating. So when you specify these design spaces, in order to work with an optimization engine, the design space needs to be continuous. So that means that when you slide the slider, it's not just some random stuff is happening. There should be a kind of correlation between any single input and how the geometry is changing. But of course, we can have many, many inputs, so the design space can be very complex. But as Lorenzo mentioned, there's a kind of trade-off. We want it to be complex, so we derive solutions we couldn't think of based on our own intuition. But it needs to be continuous so that that algorithm can actually make the decision. Say, hey, last time I slid the Avenue 1 parameter a little to the left, that seemed to do better, so I'll try that again, maybe changing some of the other ones. Okay, so that's pretty important, the continuity of these parameter spaces. Although, just because they're continuous doesn't mean they need to be totally smooth. We have here program avenue parameters, which is a Boolean or a kind of integer selection. So each program out of 3 is actually picking the avenue it wants to be placed on, either 1 or 2. So you can see that update as well. And then once it picks the avenue, each program can also, with a slider, position itself on that avenue. And then there's other kind of geometry parameters which are held as constants. So we don't need to vary each one of these during the optimization process. We can have constant parameters and we can have changing parameters. So as you'll see, the definition of this design space looks just like any other parametric model you might use in your practice. But the key to thinking of it as a design space for exploration through an automated algorithm is being very careful about the specification of the input parameters, the knobs or the genotype that the algorithm tweaks during the optimization process. With traditional parametric design, it's made for us as designers to vary those, but here we need to think about how to specify them for the computer. Okay, so once we have those parameters, they get fed into this layout node. So this is a first example of how we can start to customize Dynamo for our own needs, and we do this a lot in our practice. Dynamo is a kind of platform for us to develop our own solutions. We can develop those solutions by stringing together existing nodes that you find within the libraries here, or creating our own functionalities through code. So this, in particular, this node is responsible for the entire process of taking this floor plan and subdividing it into these regions. And we do that through direct access to the Dynamo source code. So this is one way in which Dynamo is very useful. It's completely open source. So if you want to develop your own node or functionality, you can dive directly into that source code and create your own nodes. So you can see on the GitHub repository, all the code of Dynamo is there. So from this node, you get the geometry of the blocks and the program locations. For this part of the graph, we're actually just processing that geometry. So here we're converting those polygons to points and lines. And then in these series of nodes, we're taking the edges of the polygons and we're converting them to a graph representation. So the graph representation allows us to trace people or to compute the predicted paths of all the people through the space. And this is the second way in which we can start to customize Dynamo for our own solutions, is actually through writing Python code. So this is a bit of a lighter weight use of code within Dynamo. You don't have to dive into the source code and use C#. If you're more familiar with Python, there's actually a Python node in Dynamo. It gives you a script node here. You double-click, and you can start writing Python code directly. You see here one of the first lines is the importing of the design script geometry module into this Python code. So all of the design script geometry commands that are exposed in the included library are also replicated in this Python interface, which makes it really easy to use. So here I have some code which is generating the graph representation. That gets passed to another node, which actually calculates the routing, the trace, the shortest path from each start and each endpoint. And here's another interesting tidbit here. I'm actually importing a library from my local folder, which contains some basic code for routing, which is called the Dijkstra algorithm. It's a kind of classic shortest path algorithm. I've actually written that as a Python file here in my library, and I'm able to import that directly into this Python node. So you can create your own Python modules outside of Dynamo and import them and use their functionality as a library directly within this Python node. So here in the output, we have a data set, which is the graph representation that's storing all the traversed lines in the plan. So all the information about how many people are walking through each intersection and each line is generated here. Then we parse that data format to get the actual geometry out of the lines and the points and the number of people. Let me just do something quick here. So the watch node allows us to query these things. So here we have all the points of every intersection, and here we have the actual traversals, the number of people walking through each point. Then there's some kind of utilities here, and here we get to the meat of the back end of the definition of the design space, which is computing the metrics. So the computing of the metrics is also part of the design problem, and that's very important to us as well. There's no standard way to think about quantifying or valuing an architectural design. Of course, we all value design differently, but the key here is to use the generative design process. We need to tell the computer very explicitly how we value each design. In our case, we want to maximize this idea of buzz that we kind of came up with on our end, and exposure. So there's nothing universal about these measures. And in a similar way, just like we have to come up with what those are, we have to code them by ourselves. Again, we have Python code, which is handling that computation of the buzz and exposure metrics. And in the end here, you see two windows that compute that raw score. So this is the key of the generative design process. You can use these algorithms to explore a wide range of designs, but it's just numbers in and numbers out. You need to tell the computer exactly which parameters it can vary to create different designs. You need to tell it a list of numbers to either minimize or maximize according to your preferences. So those are the blue parts here. The green parts are all visualizations within Dynamo. So in the latest versions of Dynamo, visualization has gotten a lot better. You can work with colors, also sizes and line weights and things like that. So you can see that here is the visualization of the nodes, the blocks with the orange, and the lines with the red thickness. So that's basically it. At the end here, we have some custom nodes that we wrote also in Python to actually export SVG images of each design. So we can take the designs here, and just like we're visualizing them in the Dynamo interface, we can export individual images of each one, but as scalar vector graphics, which allow us to look through the designs later and also visualize them. OK, so that's the setup of the model. We can come back to this if you guys have any questions. Let me just skip forward to the optimization part right away. So to do the optimizations, there's a variety of tools. There's actually a library built into Dynamo called Optimo that you can use. In RStudio, because we're kind of like expert users of these kind of algorithms, Dale has been working on, for the last year or so, in-house optimization platform called O2. This is a kind of external library that can interface directly with Dynamo to run the optimization. So I'm going to do a kind of baking class demo here where I'm going to run the optimization. We'll see the designs generating, and then we'll cut quickly to the visualization of the final optimization run. Okay, so very simple, O2 run. We start the process. Now, O2 is actually launching a headless version of Dynamo in the backend, so you won't see the designs changing here. It's actually a separate Dynamo process that's launching the model, tuning those parameters, and getting the outputs out. So you see here the designs getting generated. We started with the second generation. So this is a run that was already done before, and we're just restarting it at the second generation. Here you can see the 9 inputs being generated and the 2 outputs coming out, and you can see how fast each one is executed. It's pretty fast here. We can run 10,000 designs, like 100 by 100 experiment in a few days. But again, this can be easily parallelized. Now let's see the data we're producing. I have this folder here where we're actually dumping out the screenshots. So we have the input generation, the first generation here. And right now we're running the second generation. And these are the designs that we've run so far. And each one is an image of that design generated. So we have these images to visualize each design. And we also have a data set stored in a database in O2 that's containing all the data of each design. Okay, let me just cut quickly to visualization. So once we do a run of the optimization, we can see all the results. And to visualize the results, we've actually written our own web app that basically pulls in data from the experiment. So here's the kind of raw data after a run has been finished. You see the kind of ID and the generation numbers. And then this kind of raw data for each design, which is a row, you see the 2 objectives here, and you see all the input parameters that we were tuning. So we have this raw data, and we have a correlated set of images here. So we have all the SVG images that we generated. We have the data here. And then this is our web app. So it's very light. Every time we do an optimization, we generate this package of material, and we can launch this web app. And this web app allows us to explore basically the design space as it was explored by the algorithm. So for example, we can look, one of the most useful analyses is looking at the trade-offs between multiple objectives. So here we can plot on the x-axis the buzz metric. So we're trying to go higher here. And the y-axis, the exposure metric. And we can even ask it to isolate the most optimal designs based on that trade-off. And as we hover over these, we can see the screenshot visualization. And for example, we can see a high buzz design, which the routes are kind of going everywhere and dispersing the amount of activity in the space, versus like a high exposure one, where maybe there's not such a dispersal, but a large majority of the spaces are evenly activated along their perimeter. So this is a dynamic visualization. We can also visualize, for example, the sensitivity of input parameters to outputs. For example, we can look at one of the avenue inputs versus buzz and see that there's something in the lower range of that metric, which equates to higher buzz. We can also use color and the size of the circle to look through these designs. We can select certain designs. So this is as a demo fail, by the way. So as Lorenzo mentioned, especially when you're working with multiple objectives and trade-offs, the design process doesn't start with the optimization, and it doesn't end there as well. Before we do optimization, we have to take a lot of care to design our design space models and evaluate them. And then once the optimization is done, it's up to us as the human designer again to look through the results and figure out how to select our best designs. And in RStudio, we follow this process a lot. And the way that we use the results of the optimization to craft the final design is also varying. So sometimes there's a single design that's the most promising, and we take that and we kind of refine it further with additional design criteria. Sometimes we just use this process to explore a range of designs and learn some kind of techniques or strategies that are actually quite useful. For example, here you see these diagonal blocks are maybe good for exposure, and these square blocks are good for buzz. I don't know, but we can actually use this as a learning tool to study the design problem itself and come up with general strategies to solve it, and then we later apply those strategies in a more manual process. So there's no kind of secret weapon here in terms of getting the computer to design things for you. It's just a process that lets us use computation to explore more design options, but at the trade-off of being much more explicit. So before these algorithms can do their thing, we need to be very explicit about how we set up the design problem, how we tell the computer about the design problem, how to evaluate it, and then, of course, running these optimizations. Okay, so I think that is all I'll say for now. We left 10 minutes for questions. So if you guys have any questions, general or specific, all these things are up here, and we can dive in. Any questions? Yeah.
What are the actual design itself checks?
The quality of the design space or the quality of the individual design in the design space? Yeah, that's a big question. I mean, that's something that we think about a lot. I think as designers using these tools, that's the most important question. Is like, if we traditionally our design education is to value individual designs. We know how to value a certain design. We should start to develop that theory for a design space as well. Like when we design these design spaces in Dynamo, we should be able to know, like, is this a good one or a bad one? Not just like, do we have enough parameters to make the optimization run? I mean, you can do that with any Dynamo graph, right? So that's why we've been thinking of these kind of trade-offs as a way to analyze that. I think you have to think from the perspective of the algorithm. When you're thinking about creating like a design space that's broad enough to somehow potentially contain some areas of valid designs that you may not see, so you have to give it enough freedom to discover those things. But not so free that it creates a lot of garbage designs, So that's the kind of bias versus variance trade-off. But I think it's a kind of exploration process as well. Like you might not know to start with if it's a good design space. A lot of times we'll create a design space, we'll let the optimization run, see how it's exploring it, stop the process, do these visualizations, say, hey, there's a kind of pattern that seems to be converging too fast. Maybe we should look at the other area, and we discover that there's a mistake in that process. So I think in the most interesting way, you can think of it as a co-creation with the algorithm, that you craft the possibility of the design space or the boundaries. You let the optimization explore. You look at what it's explored, and then keep crafting the design space from there. I think of a kind of fly in the dark room. Like it's hard to say where things are or what the possibilities are until you start exploring, and then you kind of feedback. I'm not sure in this case if we did, but the question was whether we actually plugged in the previous AU designs from 2016 and 2017 to see how they performed in our metrics, and whether that would suggest a third metric, which was...
That was my question for you.
Okay. Yeah, that's a really good question. I'm not sure if we did in this case, but we have done that in other projects. This was a big component of our project for the new Toronto Autodesk office because we were designing for a group of people that already had an office and were already working together, and we're going to move to this new office. So we had actually, in the same way we crafted these metrics, but in order to validate them, we had an existing space to work with that people knew very well. So in that case, we did model their existing office space and did interviews and validation rounds. So for example, we would run our algorithms to score the space, and would ask for people for their intuition, like, is this in fact seem like a busy area of the office as predicted? So I think that's really important to do, especially in the kind of bigger, longer term project where it's really important that what you're predicting and basing your final selection on is in fact valid. Yep. Lots of questions. Lorenzo, you pick one. I take no responsibility. Yeah, so I guess I should say that the bias versus variance trade-off is part of the machine learning literature, that we kind of adopt that terminology. What we're talking about with bias is specifically like the bias of the model towards creating a wide variety of designs. So for us, a model that's too biased is too constrained. So for example, it could be constrained by common rules of thumb that we say like food cart should always be by the bathroom or something like that. And I think, yeah, there's no right answer. I think when you're developing these models, you really have to look at which constraints or which rules of thumb you input as a bias into the model because you know it should be so. Because not doing it would create so many invalid designs or just break the rules so much that you spend the whole optimization process filtering through dumb solutions. And which ones you start to let go because you wanted to explore something you might not predict. I don't think there's a right. I mean, it's a really important question in terms of how we acknowledge the biases in our design processes, and that's the really kind of opportunity of these workflows is that we can sort of relax some of those rules and let the algorithm tell us where the good designs are. But I don't think there's a specific answer. It kind of depends on the model you're working with. In our case, what the bias, the constants were the number of programs. So we talked to the organizers and we created a kind of exhaustive list of all the 10 or 11 programs that had to be in the space. So that was the bias, I guess, that there was always 10 or 11 programs, and they all had a certain size, and they were always located in the floor plan. And that ensured that every design in the design space was valid from their point of view, because they're like, we just need these 10 spaces. Everything else was allowed to vary, subject to the geometry which was generated. So based on the subdivision of the avenues, each program would locate itself on the avenue, and then the circulation, everything would result from there. Yeah, we didn't have any of these more nuanced things about co-locations, but we could have built them in. I think what you're talking about is a kind of conditionals and if-thens are like a really good strategy to create complexity in the design space. Because the more relationships you build in, a lot of like kind of unexpected things can happen when those rules get enacted. But also the more specifically you encode these things, the more bias you build in, because then you're like kind of constraining the design space more and more. And on the far end of variance, you can say everything is allowed to be anywhere, and you just have like a separate parameter for the position X and Y for each program. But then, then maybe the design space is too big. Yeah, so in the case of more than 2 objectives, basically the trade-off space gets much deeper, right? There's a kind of technical answer in multi-objective optimization. There's a way to look at high-performing designs as those that are better than all other designs, at least in one parameter. You can imagine if you start adding parameters, it's more and more likely that some design is going to be better than at least one and probably worse than others. So it does get more complex from an interpretation standpoint. From a technical standpoint, it's the same exact tools. Actually, this visualization works with any number of input or output parameters, but you don't get a simple, nice chart. And part of the reason we were like constrained it to 2 objectives is to be able to visualize it very clearly, because the AU project was a kind of demonstrator of the process. But as Lorenzo mentioned, in almost every other project we've used this kind of workflow, there's many more objectives than just 2. But I think also there, you can work with the model definition. Sometimes you can fold multiple objectives into a single objective if there's a relationship between the 2. But yeah, basically the kind of post-processing or exploration part can become more complex if you have a lot of objectives. One tool we use is like weighting. So after when the optimization is running, you don't want to constrain too much the algorithm. You want to just explore potentials and all these different trade-offs. But after it's run, you have the data set, you can start to weight those objectives. So you can say that, well, for example, buzz is much more important. And you can re-weight those things and rework the visualization. You can also combine the different objectives with some kind of weighted equation, and then they'll give you one result. So if you say that buzz is twice as important as exposure, you can put that into a kind of weighted equation, and it'll give you one design where buzz is twice as important. This one is currently running just on a local server. Oh, no, it's custom D3 code. Just Python. There's a lot of ways you can speed things up with libraries, but in our case, all of this stuff is written at a kind of low-level Python code. And also Lua and C#. Yeah, the built-in nodes are in C#, and the kind of Python code embedded with the node is Python, obviously.